Hello and welcome to this clip on redox half equations and disproportionation. These are both ideas that take you slightly beyond the emphasis on the first year redox ideas and start to lay the groundwork for taking redox into the second year of the A-level chemistry course. So before going any further, it's worth just doing a quick review of the oxidation number assignment rules. So the general rules are listed on the screen. If you're watching this clip, hopefully you've already got a copy of these either in your notes or perhaps on flashcards, and you're some way towards understanding or at least remembering them and being able to apply them. Now there's a few exceptions that it's worth quickly mentioning. So hydrogen is an oxidation number of -1 in hydrides. Oxygen is +2 in F2O or +1 in peroxides. We'll come back to a peroxide a little bit later on in the clip, so I'll leave that one for now. Let's think about why oxygen is +2 in F2O. So if you take the F2O molecule and you assign the oxidation numbers, you'll need to remember that the neutral compounds must have all the oxidation numbers add up to 0. So fluorine is assigned -1 in all circumstances because it's the most electronegative element. So if fluorine is assigned -1, and there's two of them, that means that to make the compound neutral, oxygen would have to be +2. So looking mathematically at it, each fluorine atom has an oxidation number of -1, so two lots of -1 gives you -2 in total. So in the case of oxygen, only one oxygen atom is present, so this must adopt an oxidation number which balances out the -2 to make the overall charge 0. Hence oxygen must be +2 in this case. So moving on to group 1 and group 2 elements. These all get the same oxidation state, positive sign, as the group number. So group 1 is +1, group 2 is +2. All uncombined elements, including diatomic molecules such as N2, H2, Cl2 for example, are assigned 0. Single ions such as Cl-, Na+, etc. are assigned the charge of the ion. Neutral compounds must have all the oxidation numbers adding up to 0, like we've just said, and polyatomic ions must have all the oxidation numbers adding up to the overall charge on the ion. So here we've got a sodium atom and a fluorine atom with what needs to take place in order for each one to achieve a full outer shell configuration. So obviously, when they react, what needs to happen is the sodium electron is going to move off the sodium atom onto the fluorine atom. So that means the sodium atom loses an electron and the fluorine atom gains one, which in turn means the sodium is oxidized and the fluorine is reduced. So we call sodium the reducing agent and fluorine the oxidizing agent. So sodium has caused fluorine to become reduced, fluorine has caused sodium to become oxidized, all because of that simple transfer of an electron. So we can write out what we call a half equation to represent each process. So on the left you've got sodium losing an electron to become Na+, and on the right you've got fluorine gaining an electron to become F-, or a fluoride ion. Now we've got to be a little bit careful at this point because we know that fluorine doesn't float around as just F. It's a diatomic element, so it floats around as F2. So in reality we'd have something like that going on. That now means the electrons aren't balanced on each side. You can see there's 2 on one side and 1 on the other, so we've got to balance it out on the sodium side as well. So now we've got two half equations. It's an exchange of 2 electrons. So a fluorine molecule, F2, takes 2 electrons from 2 sodium atoms, 1 from each. So we can now combine these two half equations. So if you look at the top half equation, the oxidation, and the bottom half equation, which is the reduction, you can see that there's 2 electrons that can be cancelled out. So if you cancel these out and you add up all of the things that are on the left hand side to all of the things that are on the right hand side, you can now end up with an overall redox equation. So obviously sodium is a solid, fluorine is a gas, and you know that sodium fluoride would be an ionic solid, so you put the appropriate state symbols next to each species. Now you can even use oxidation numbers to prove that oxidation and reduction has taken place here. So by putting in oxidation numbers above each element, you can then trace what happens to each one. So, starting with sodium, you can see it goes from 0 to +1. So putting this into words, you say sodium has been oxidized from 0 in Na to +1 in NaF. So doing the same this time for fluorine, we say that fluorine has been reduced from 0 in F2 to -1 in NaF. So all through this clip so far, at the top of the screen I've mentioned something called disproportionation. Let's now have a look at what this actually means in practice. So taking the same idea, this time why not pause the clip and see if you can put in the oxidation numbers for each of the elements on both sides of the equation, and then see if you can work out what element is disproportionated. So hopefully you got something similar to what I've put there. Now we can take the same idea using the arrows. So hopefully now you can see that the same element, oxygen, is being simultaneously reduced and oxidized. So, how does this work? So on the left hand side you have a total of 4 oxygen atoms contained within 2 hydrogen peroxide molecules, 2 of which are reduced and 2 of which are oxidized. So we've had a simultaneous oxidation and reduction of oxygen going on, and oxygen was in the same species, hydrogen peroxide, at the beginning. Now there are quite a few examples of this that happens. The key thing to look out for is the same species having more than one of the same atom, and one of the atoms goes on to be reduced and the other atom perhaps goes on to be oxidized. To illustrate this, it's time to have a go at an exam question. So you might want to grab a piece of paper or a whiteboard and try the question when I bring it up on the screen. So looking at this question, it tells you already that it's a disproportionation reaction. You can see within the question. So what I'd like you to do again is pause the clip and see if you can work out a possible answer to not just the first part, which is quite straightforward, but the second part using oxidation numbers that you've just worked out. So do part 1 first, then part 2. So you can then resume the clip once you've finished your answer and we can take you through it. So if we start by looking at the equation and assigning oxidation numbers, you can see that in HClO, chlorine is made to take a +1 oxidation state. So we can now work out what's happening in each case. So before we do any arrows or drawing of lines or anything like that, let's look at what isn't changed in its oxidation state. Well, first of all, you can see there's no change in hydrogen. There's also no change in oxygen. If we now put the lines in, you can see quite clearly that chlorine is disproportionated. So each atom in the chlorine molecule on the left-hand side has had a separate thing happen to it. One has been reduced, one has been oxidized. So now we can put the oxidation numbers in our answer. So in the second part of the question it says use the oxidation numbers in part 1. So what that means is we've got to refer to them. So let's start with the reduction. So chlorine has been reduced from 0 in Cl2 to -1 in HCl. And it's been oxidized from 0 in Cl2 to +1 in HOCl. So when I'm putting it into words, I'm making sure I've got the starting and finishing oxidation numbers. And I've also included the starting and finishing chlorine-containing species linked to the oxidation number. So just to clarify that, starting and finishing oxidation numbers and starting and finishing chlorine-containing species. So just to finish off, let's have a look at the mark scheme. So chlorine has been both oxidized and reduced, or its oxidation status increased and decreased. And it's been oxidized to +1 from 0, and it's been reduced from 0 to -1. Now notice what we didn't put in our answer was this. So we didn't actually say in words it's been both oxidized and reduced. But if you look a bit further down, it says those 2 points together subsume the first marking point. So what that means is, provided you say both of the things at the bottom, you'll get 2 marks. Okay, so hopefully this has been a fairly useful introduction, or extension rather, from Redox in the first year into half equations and disproportionation. So in the meantime, thank you for listening, and hopefully see you soon.